Hi there, another rather large piece of vintage equipment from eBay. This is a MARCONI Universal Bridge TF2700. I have not done anything with this and have no idea if this works or in what condition it is. You are experiencing this at the same time as I do. As you can probably guess from the stuff written on the front panel, this is an LCR meter of sorts, where L is measuring inductors, C for capacitors and R for resistors. Some markings by the previous owner in fluorescent paint on the top. Nice. I think I will try to tone that down a bit. A large dent on the side. But the back looks rather clean and tidy. No power inlet, that is obvious. How is it powered? I decided to open these two screws on the rear. Oh dear, this is not very nice. A totally corroded battery that must have been there for ages. Loose battery terminals. At least the battery moves and is not stuck. I think it will come out when I tilt it. And yes, it does. Ever ready? Well, not anymore, I guess. This is a PP9 9-volt battery and its terminals have corroded off. I wonder what it did to the bridge itself. Okay, this may not be as bad as I thought. It looks as if the battery compartment is a plastic box by itself which contained most of the damage, so hopefully it did not spread into the unit. The battery terminals are actually still inside the battery clip. The rear of the battery has a code, probably September 1995, nearly 20 years old, but this could be the expiry date, so it might even be older. These batteries are still available. I could get a new one easily. Maybe I will do this if the unit itself is working. Out of curiosity, has it any charge left? The terminals are gone, so I poked the probes into the holes where they have been. About 50 millivolts, so the answer is not really. And now it's high time to get rid of this thing spreading gunk everywhere. How to proceed with the teardown? There are 4 screws on the rear. The most left one is already half out. I am slightly worried that if these hold some components inside, you do not want to open them. And then there are 4 screws in the feet. I decided that the screws at the bottom are probably okay to remove. So let's do them. The 4 bottom screws are out. And the bottom plate is moving, but the enclosure as a whole is not. And without that, even the bottom plate can't be taken out. So there's nothing for it but to try the other 4 screws in the rear panel. And yes, once they are gone too, the whole inside can slide forward. I can put the rear enclosure away and have a good look at the inside of the MARCONI TF2700. But first, the bottom plate. Some weird stuff lying here. Hopefully these are just things that somehow got in through the vents and not some part of melted electronics. On the side is a PCB with the actual active part. Looking not too bad. A few caps, 3 transistors, a couple of resistors. Some very cool slider pod. I've never seen one of these before. The slider position is actually fixed with lacquer, probably after some calibration. Some more components on the other side of the housing on some terminal strips, coils, capacitors, resistors and another transistor. The front panel with its range switches, meters and potentiometers. All very complex but very neatly done. And then there is the black box containing the battery and quite literally containing the mess it made when leaking. I have to congratulate MARCONI for the foresight of putting this in. Imagine the battery corrosion would have spread into all these complex circuitry. It would have been beyond repair, no doubt. After removing the bridge, I discover more mess on my workbench. All things that had fallen out while examining the interior. The white stuff is plastic, styrofoam to be exact, and likely from the eBay seller's packaging material. I'm more worried about the black stuff, but I can't figure out what it is and where it came from. Hopefully not from the electronics. I guess we'll find out. The first repair job is easy. The power on and mode switch is obviously in the wrong position. This I can fix. Sorry for the blurry video. When the switch is in the off position, it covers the red segment. Once you move it out to one of the other positions, the unit is on, and then the visible red segment serves as a reminder, not eating any additional power that an on indicator with an incandescent lamp would have used. No LEDs in those days. To test if any further repairs make sense, I want to power up the unit using my bench power supply hooked to the rotten battery connectors. I studied the circuit diagram in the service manual, and therefore I know I should see a 1 kHz sine wave on the two terminals in C or capacitance mode if the oscillator in the unit is working at all. Let's see, power on, and something is happening on the scope. Just need to adjust the gain to get a larger display. Yes, there it is, the oscillator is working. That's a great start. I want to briefly explain the front of this machine because at first glance it looks scarily complicated. The capacitor, inductor or resistors are connected to these two terminals. The function switch selects between capacitance C, inductance L, and the three resistance modes R. One uses AC, the other DC from the battery, and the last uses external DC power. For C, L and R in AC mode, the meter normally uses the internal 1 kHz oscillator I showed earlier, but you can replace that with AC from an external generator using this connector. These are for normal 6.3 mm mono jacks like those for electric guitars, so nothing exotic. A similar jack can be used to feed a bias current in. Better LCR meters offer this because some caps and large inductors have different values when operating with a bias applied. The bridge not only measures capacitance or inductance, but can also give a rough idea of the D or Q value. This is the loss factor. D stands for dissipation factor and is the reciprocal value of Q, which is the quality factor. The better the quality Q or lower the dissipation D, the better is the capacitor or inductor. The small knob selects between two D ranges and Q. For large electrolytics or transformers, D works best, but otherwise it's a bit of trial and error. The idea is to balance the bridge so there is no current flow between the two branches. I made a video about a strange box that turned out to be a bridge to measure resistances only, and in there I explained this principle in detail, so I skip going over the R modes in this video. As in all bridges, you want the meter to show 0. In AC mode, the needle only goes to the right, but in DC mode it can swing both ways. The sensitivity of the meter is selected by the dial down here. When the bridge is not balanced, selecting a sensitivity where the needle shows some deflection but isn't at the limit. Then, as the bridge gets more balanced and the needle gets closer to 0, the sensitivity can be increased. Finally, the process itself uses the range switch first to select the likely range. If unknown, you can simply try one after the other and pick the one that has the lowest needle deflection. Then use the balance control knobs to narrow the value down. Balance control has an outer ring and an inner knob that allows fine adjustment to 1/100th of the outer ring value. After getting a minimum on the balance control, adjust the loss balance to try getting even closer to 0. If that worked, then it's back to the balance control for a finer adjustment and so on until you can't get any more improvements. After all this, you can read the values for C, L or R on the balance control multiplied by the range setting and an approximate loss factor Q or D from the loss balance knob position. I put an electrolytic cap across the terminals and let's see if this thing can bring out its value. As a start for electrolytic capacitors, the manual says to select D rather than Q. Next, adjusting the sensitivity to get a medium deflection, so it's easy to see if adjusting the range or balance control improves things or makes them worse. Remember, lower needle deflections are better. Just cycling over the range and it's clear that the deflection doesn't improve at smaller values, but it does towards higher ranges, and in fact it's already almost 0 at the 1000 microfarad range. So the next step is to increase the sensitivity to get a good deflection again. And to try the outer ring of the balance control. The current value is shown through the clear window with a horizontal line on the left side of the knob. Going backwards and forward a bit, the 0.2 position gives the lowest deflection. Time to increase sensitivity again. Adjusting the fine balance control gives only a slight dip in the needle. so I switch over to the loss control knob instead, and that has a significant effect. So much that another increase in sensitivity is needed, but we're already at nearly the max. Anyway, now it's definitely maxed. Moving the balance control backwards and forwards a few times to establish where the needle is lowest. And what result have we got? The large ring reads 0.2 and the inner one a little more than halfway between 80 and 82, let's say 81.5. So considering the range was 1000 microfarad, we have 1000 microfarad times 0.2815, that is 281.5 microfarad. The D value is essentially 0. Maybe I should have tried the times 0.1 D position, but anyway, the indication is that this capacitor has a low dissipation, so still good to use. Here's a close-up of the capacitor. It's nominally 330 microfarad and we measured it as 281.5 microfarad, which is a little low, but given that electrolytic caps usually have a 20% tolerance, anything between 396 and 264 microfarad would be in spec. Using my transistor tester from a previous video, now in a housing, it shows 279 microfarad and 0.14 ohm ESR, closely matching the 281 microfarad reading the bridge produced. Let's try another capacitor. I'm speeding this up slightly since it's essentially the same process you have just seen. Selecting a good range, followed by moving the outer ring of the balance control, and 0.0 seems to be the lowest. The loss control did not do much. Trying the fine adjustment of the balance control, I'm actually over 100 already, so it's better to move the outer ring to 0.1 and start the fine adjustment from the other side of the scale. So we are in the 1 microfarad range, the outer ring reading is 0.1 and the inner one nearly at 0.8, say 0.7.5, so in total we have 107.5 nanofarad. D is at 1, but since we're already in the 0.1 setting, it's actually 0.1. The transistor tester says 101 nanofarad, which is not as close as I expected it to be, but the tester uses a different method and frequency to measure capacitance. So I brought out my big LCR meter, also using 1 kHz, and that says 104.49 nanofarad, nearly exactly in the middle between the other two. Checking with 3 meters and get 3 different values. I was wondering if that trend continues, so in no particular order I grabbed every meter in the house that can do capacitance, which are embarrassingly many, and tested the same capacitor. The Fluke 187 says 104.8. The Primon BM869S says 105 or 104.9. The Aneng 870 says 104.9. The Kaiwitz HT118E says 104.69. The E model is the 20,000 count follow-on model of the HT118A, that's why we get 2 decimals. The O1X DM1041 says 104.1. The O1 HTS272S fully agrees with the Kaiwitz down to the 2 decimals. I wonder if they use the same chip. My trusty old Primon BM235 says 105.4. The tiny Fluke 101 says 104.5. The Unity UT210E sides with the BM235 and says 105.1. The TTI 1705 can't decide between 105.1 and 104.9. I take 105.0. The Sanwa PM3 is a pocket multimeter that lives in my backpack and travels wherever I go. Its leads are not removable, so I have to use them to measure the same cap. It says 103.8. The Unicore 6E has a capacitance mode, but to be true, this is the first time I'm using it. I picked the 100 nanofarad range. I need to zero it first with no cap attached. The needle goes to 1, that is 100 nanofarad. The scale is too small to see if it's exactly 100 or maybe 105. Apart from the realization that I have way too many multimeters, the result is interesting. I plotted the values as a stock graph, so the horizontal lines are the measurements and the vertical bar is the possible error margin of that measurement according to the spec of the meter. I don't have the accuracy spec for the transistor tester, so there is no vertical bar. The consensus of the majority of the meters seem to be around the 105 nanofarad value, in particular the 10 MAR, the Beam 869S and the Fluke 187 have fairly small error bars and are all just below 105. I marked this with a red line. The TF2700 is further away from that line than I expected because the specified base accuracy of the bridge with 1% is quite good. I mean, theoretically it could be that the bridge is right and all the other meters are wrong, but given the majority of the meters all agree, that's very unlikely. An error in the TF2700 or in the way I was using it is more likely. I studied the manual in greater detail and then realized that the large error is due to the fact that I measured the 100 nanofarad in the 1 microfarad range, because while the accuracy is 1%, there's an additional 0.1% of the full range to be added. What I missed is that the bridge range control actually goes from 0 to 10, not 9, so you can actually measure 100 to 199 nanofarads in the 100 nanofarad range, which is what I'm doing here. The result is 100 nanofarad times 10.41 or 104.1 nanofarad. That looks a lot better. Of course, if the cap was 200 nanofarad or above, you would have no choice but to measure it in the 1000 nanofarad range, but the relative error would not be as bad as measuring 100 nanofarad in that range. But enough of capacitance, let's check an inductor. The process is exactly the same, just the function knob is put to L. In the interest of time, I accelerated that a bit. Searching for a good range indicates 100 microhenry as a good one because the meter dips lowest. Spinning the outer balance ring shows the lowest dip at 0.6. While doing the fine balance, I realized that I was in the D times 0.1 mode and had maxed out the D. So I switched to the D times 1 mode to get a proper dip for the loss balance knob. The dials are quite sensitive in this measurement. The tiniest change produces a big needle movement. What have we got? We are in the 100 microhenry range. The outer ring says 0.6 and the inner one 74, so in total 67.4 microhenry. D is hard to see but nearly 0, which means low losses. Connecting this inductor to the transistor tester shows 50.4 microhenry. The only other thing I have that can measure inductance is the 10 MAR batch UT612. That shows 66.4 microhenry, which is pleasingly close to the bridge result of 67.4 microhenry. I guess one should not expect too much precision from a transistor tester. Having a second accurate measurement device for inductance was one of the reasons why I got the TF2700 bridge in the first place. But there are more reasons. For example, I can use any frequency between 20 Hz and 120 kHz if I feed it in externally. Many caps are rated at 120 Hz, not 1 kHz. The manual recommends using an isolation audio transformer, and I happen to have a tiny 600 ohm one lying around. That turned out to be trickier than I thought, because using the bridge outside its case and all my non-shielded test wiring introduced too much noise to demonstrate any useful measurement. Case in point, watch the meter, it is swinging by itself. The reason is that I'm feeding externally an AC that is just slightly higher in frequency than the mains hum of 50 Hz, and the meter amp signal varies with the beat frequency between the two. I can make it swing faster if I increase the external frequency. The point is, I need to make myself a totally shielded transformer and cable setup to avoid getting mains hum into the amplifier in the first place before I can use this feature. Another reason for me getting the bridge was that it allows adding bias. All LCR meters normally warn you to make sure caps are discharged. Well, here I can actually charge them while measuring. I demonstrate that with a voltmeter across the cap, which of course has to be removed when measuring. Some caps and ion-based inductors can change behavior if they are charged, or, for inductors, a DC current flows through them. The DC bias you just saw came from another bench power supply over a fairly long cable, so I struggled with the same noise problem as mentioned before, and switched to the battery supply here. You also see that there needs to be a safety resistor in series to protect the bridge resistors and a large cap to let the measurement AC pass through. In my test of the same electrolytic cap of 330 microfarad I used before, I did not see any difference in capacitance when biased by 9 volts DC, but then the manual says the effect may take a long time to manifest itself. I will try that another day. Now I want to fix the mess the old battery left behind and put that thing back together. This is the back plate after I cleaned the battery gunk away as good as I could. The metal is left pitted as a result of the battery chemicals. There was a kind of foil, I guess for insulation between the metal and the battery. That foil is beyond fixing, so I decided to use a leftover piece of laminated paper to make a new one. I spent quite some time cleaning the battery compartment itself. That is a very sturdy plastic box and showed no signs of deterioration. Of course, my cleaning actions to remove stuck gunk with sandpaper left some marks, but I can live with that. One of the worst affected areas was this bottom bar of the outer casing. I spent at least 2 hours with sandpaper trying to remove all the battery stuff. I hooked up a meter to show the current drawn by the bridge when fed 9 volts from my bench power supply. It varies between 3 and 6 milliamps depending what function and range is selected. The DC resistance mode is of course the most power hungry one. With such low power draw, there's really no need for a massive battery, and I could just replace the old clip with one for a standard 9V PP3 battery found everywhere, fill the huge battery compartment with bubble wrap, and leave just enough space for a small 9V battery. But the other day in a hardware store I saw PP9 batteries for sale, and out of a whim I bought one. So at least for now, this is what I will use. Of course, the 2 old and corroded connectors have to be replaced with a new one for PP9. Off they go into the garbage. The new clip is installed, and I thought I'd just test if it's wired correctly using the bench power supply with the current meter from before still attached. And I was in for a surprise. The previous 3 milliamps is now nearly 6, and some resistance modes draw 36 milliamps. I had not realized how corroded the old connectors were. There must have been quite some contact resistance. It's interesting that even with the power reduced, it measured C and L just fine. It probably would have failed on arm measurements with DC. Sadly, the bridge has no built-in battery test. The manual says you need to use an external volt or current meter following this procedure. I actually did this while using my bench power supply and the corroded terminals, but I used a voltmeter and that was reading nearly 9 volts. So of course a high impedance voltmeter is not detecting a few ohms of contact resistance. But if I had measured the current, that should have been revealed. Well, now I know. Given how hard it is to test after installation, how much voltage does a new PP9 battery have? Wow, over 10 volts. I put the enclosure back on and the new battery is in and connected, which means I can close the battery compartment too. Because of the possibility the contact resistance of the corroded terminals could have changed my previous test results, I decided to run the 100 nanofarad capacitor test again using the new battery and connectors. Spoiler alert, there was absolutely no change. While this is running, it just remains for me to say that I'm quite happy with the TF2700. These bridges are very affordable on eBay, and since I don't measure caps and inductors every day, the slow and old-fashioned way they work is not a problem for me. These days I would not use a bridge for resistance measurements, which happen to be much more frequent and which any multimeter can do faster and usually better. If you like my videos, don't forget to subscribe, and it would be great if you decided becoming a Patreon. That would really help this channel. The link is in the description. As a Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.